So we'll start the your object down. So in the same way, inductance, instead of thinking of an inductor, okay. So just like when we instead of talking about capacitors and inductors are nothing but lumped elements, like whatever resistors, capacitor, and inductors. So when you draw like this, so this is your symbols, right, for your inductors and for your capacitors. What you're doing is you're basing saying that in the whole circuit, the inductive effect is only at this place. Okay, wherever you have winded the coil, ఎక్కడైతే coil చుట్టారో, there only you have the inductive effect. Wherever you have placed your resistor symbol, that is a location where you are having the resistive effect, or the capacitive effect is only between the plates. But usually, when we go for higher frequency devices, in higher frequency circuit designs, these effects are not lumped in some location, but they are distributed over the network. So in that scenario, it might be hard to find a kind of solenoid kind of loop, or you might not see capacitor as two plates, right? Because there we deal with the distributed effects. So you need to get out of that circle where you think an inductor is always looks like this. An inductor should always be a winded wire, or a capacitor should always have two plates. So this kind of notion you should come up. Okay. So anyways, but for understanding purpose, just like for understanding the basics of capacitance, we always start with the most easiest one, that is parallel plate capacitor. And also to understand inductance, the most easiest one is to start with the solenoid, right? So solenoid is simply a wire which is wounded around a bar, right? If you have a ferromagnetic material like this, so some kind of material, you wind a wire like this, and this is what we call a solenoid. And of course, the fields of the solenoid we already saw is that they are almost uniform inside everywhere. So the fields are uniform everywhere. The fields are uniform everywhere. We assume that there are no fields outside, though practically it is not possible. So if we assume such a scenario, we got the expression for fields also. The fields were like uniform everywhere, and the fields are given by something, I guess, mu naught number of turns per unit length. Okay. I think n is the turn density. I think what some mu naught n into I. Okay. Where n is the number of turns you have per unit length. Okay, so you can see that just like your capacitance, inside the capacitor also we assume that there is an uniform field, and that kind of approximation we start with to get the expressions for capacitance and in parallel plate scenario. So C is equal to epsilon naught A by D is only valid for a parallel plate capacitor which has only fields inside the capacitor, and even the fields inside are uniform everywhere. Then you can use this expression. In the same way, we can also get an inductance expression for a solenoid also by doing some derivations and all. But that is not the important point here. You need to understand what is this properties where I say inductance and capacitance and all. Right? So when you say inductance, usually two things. So what is this property? What do you mean by inductance is, so the ability of, it is not the ability, I can say the resistance uh, of a material for a change in current. Okay. So opposition, so whatever opposition inside a material for change in currents, right? So these currents can be anything. Okay, maybe displacement currents or induction currents, it doesn't matter. So this conduction currents or displacement currents. So what I'm saying is any kind of varying currents will have an opposition. Okay, they don't like I mean the field they create. If there is a varying flux, okay, that always tries to oppose the varying magnetic field. So inductance is a concept like if you say a material has some inductance, that means it doesn't mean, so usually we think inductance is like inducing. So we might say the ability to induce currents అంటే ఒక సర్క్యూట్లో నుంచి ఇంకొక సర్క్యూట్లో కరెంట్స్ ఇండ్యూస్ చేసే క్యాపబిలిటీని ఇండక్టెన్స్ అంటాము అని అనుకుంటాము. బట్ దాట్ కమ్స్ అండర్ మ్యూచువల్ ఇండక్టెన్స్. ఓకే. ఇన్ఫ్యాక్ట్ ఒక సర్క్యూట్లో కరెంట్ తిరుగుతుంటే ఇఫ్ వన్ ఇన్ వన్ సర్క్యూట్ a current is moving on, if I place another circuit here, so why does current go in the circuit is because only when the current is changing in this first circuit, the magnetic field around it changes and there is a changing magnetic field, and in order to oppose that changing magnetic field, nature tries to produce currents, and EMF is induced in this second coil. So this kind of induced EMF or this inductance is what we call as that capability we are calling as mutual inductance, right? So mutual inductance may be thought of as an ability of how much the current is producing, but it is not the ability of your circuit. It is actually saying how much opposition the circuit is providing for a changing field. Okay. So, in the same way, there are usually we define inductance in two ways. One is self inductance, and another is mutual inductance. So, mutual inductance happens between two circuits. If in a one current carrying wire, so in a current carrying wire, if the current is changing, okay, how much effect it will create in another current in another wire which is present beside it. Okay, so uh, how much it will start to induce the field అంటే ఎంత కరెంట్ని ఇండ్యూస్ చేయగలదు or what is the amount of current that has to flow in order to oppose the changing magnetic field somewhere which is another wire which is kept at some location. So this is what we call as mutual inductance, but there is also self inductance. Self inductance is something like whenever you connect your battery and you connect it to a solenoid, of course you might also have a resistor. So inside this before connecting before connecting the circuit, you can see that your solenoid does not have any magnetic fields inside it. Why doesn't have any magnetic fields? Include magnetic fields ఎందుకు లేవు అంటే because no magnetic fields initially. Why doesn't it have any magnetic fields? Because initially there was no current, right? Because the switch was open, so there was no current. If there is no current, then there are no magnetic fields basically. So when you close the switch, what happens is slowly the current starts to increase, but it cannot change instantaneously because if you assume that initially before closing the switch the current was zero, but when you close the switch, can I have a 3 amperes of current? No, you cannot have such a big amount of current because that means if you say your current instantaneously change it from 0 to 3 amperes, 0 నుంచి 3 amperes ఇన్స్టంటేనియస్గా చేంజ్ అయిపోయింది అంటే దట్ మీన్స్ ద మ్యాగ్నెటిక్ ఫీల్డ్ ఇన్సైడ్ దిస్ కండక్టర్, ఐ మీన్ ద మ్యాగ్నెటిక్ ఫీల్డ్ ఇన్సైడ్ ద solenoid is created instantaneously. You cannot create a field instantaneously. Any kind of field creation takes a finite amount of time, right? So in order to have a field which can support that 3 ampere, you need to do work. Okay, why your battery has to do work? Why does it has to do work? Because it is not changing the flow, because whenever you are trying to increase the current, okay, so already 0 amperes nunchi, for example, you somehow manage it to bring it to 1 ampere. Now if you want to change the current from 1 ampere to 2 amperes, that means you have to do work. Why do you have to do work? What is the problem here? Because already a 1 ampere current is flowing, and say for a 1 ampere current, through the solenoid there is already some flux. Okay, so when you are trying to increase the current, if you are trying to increase the current, then the amount of flux that is crossing through this solenoid is has to increase. So if the flux is increasing, there is always an opposition. So your inductor or your changing magnetic fields try to oppose the increasing current. So your current instantaneously will not increase, so it will take time for the current to increase to 1 to 2 amperes and 2 to 3 amperes. Okay. But whereas if your circuit was only connected to a resistor, then instantaneously your current everywhere can jump from I is equal to 0 to I is equal to 3 if you assume there are no inductive effects anywhere. I mean, if there is no time varying magnetic fields, and even though there are time varying magnetic fields, the magnetic field variation is significantly less, then we can assume instantaneously your current changes from 0 to 3. So at any point of time, okay, you have a scenario like opposition of changing currents, then we usually address it with the concept of inductance. Right, so in the same way, if you have two circuits, okay, that is self inductance, and of course we saw the definition of mutual inductance also. So let us dive back in and see what is this mutual inductance and all. So, time varying currents can induce EMF in another loop or same loop to oppose the changing magnetic flux. That is how we define the inductance. So, say for example, there is a loop 1 which is having a current I1, and it is say it is creating a magnetic field B1. So, now for example, if you put a loop 2 in this magnetic field B1, and if the magnetic field is changing with time, if you are increasing the current, then the magnetic field is increasing, then the flux crossing through this loop is basically increasing. So what happens? Uh, Whereas, I mean, what happens? What is an expression we'll see, but what is self-inductance is in your loop there will be only one loop, okay, and and in this loop, if the current is going out, and if current and flow అవుతున్నప్పుడు, if you try to increase this current now, okay, that has to increase the field that is already there, so it also changes the flux that is crossing through the surface. So there will be something called self-inductance coming into picture. సో ఫస్ట్ ఆఫ్ ఆల్ ఇక్కడ యూజువల్లీ ఏంటంటే ఇండక్టెన్స్ అన్నది ఈజ్ ఇట్ ఆల్వేస్ డిఫైన్ టు లూప్స్ అంటే యూజువల్లీ వీ ట్రై టు డిఫైన్ ఇట్ టు ది లూప్స్. ఓకే, బికాస్ యూ because the EMF is defined over a loop. So uh, but sometimes we also define inductance only for partial, we call it as partial inductance and all, where we define it for single wires and so. Okay, but anyways, that is not the part of concept which we are dealing now. You see those kind of things in EMI and EMC courses. So these are the inductance which we will be dealing with. So most of them are loops. So mutual inductance and self inductance are the most common ones which you see. So if you ask me what is the magnetic field B1, what is a magnetic field B1? And B1 is nothing but mu naught by 4 pi I1 times of loop integral of, because around the loop. So if I take cut a small piece, and this will be nothing but dl1 bar cross r cap by r square, right? So this is nothing but Biot-Savart's law. Okay, so it is Biot-Savart's law for means you calculated the field B1 for a given current I1, and this is how you do it. Now, what is the flux that is going out in the second loop? From the second loop, flux is nothing but the surface integration of d1 bar dot ds2 bar. So if for the second loop, say for example, if I get a small area and the normal to the surface is ds2 bar, then what is the flux that is going out of the second loop is nothing but surface integration of d1 bar dot ds bar. Okay, so if that is a flux, okay, so b1 bar, because but b1 bar can be written as curl of some magnetic vector potential a1, where a1 is the magnetic vector potential for magnetic field b1. Okay, so if that is a scenario, you can see from the curl theorem, from the Stokes theorem, surface integration of curl dot ds2 bar is nothing but loop integral of a1 bar dot dl2 bar. So you can see that you can actually calculate the flux in the second loop either using magnetic fields, or you can also do it with the magnetic vector potentials. So let me go and do with the magnetic vector potentials, but you know that for a given current density, the magnetic vector potential expression is given by, for a line current, it is nothing but mu naught I1 divided by 4 pi and line integral on this path. Okay, so you're basically doing line integral on this path. So dl1 bar divided by R. Okay. So if this is the case, I can substitute this expression here. Okay. So if I do that, you can see that in terms of A1 bar, I have placed the A1 bar expression. And what I can see here is you can actually rearrange these terms in such a way that there are two double integrations dl1 dot dl2 by r into some I1. So I brought this I1 onto the other side. So if you see, if your current is varying, okay, if your current is varying, if your I1 is varying, then the flux will also vary with time. Okay, your flux also starts to vary with time. So ఎంత వేరీ అవుతుంది సో ఐ కెన్ సే దట్ ఫ్లక్స్ ద అమౌంట్ ఆఫ్ ఫ్లక్స్ ఇన్ సెకండ్ లూప్ ఈస్ ప్రపోర్షనల్ టు ద current that is flowing in the first loop. So what is a proportionality factor? And this is your proportionality factor. So this thing which is in this box is nothing but the proportionality factor. So for a given current in the first loop, how much current in the second, how much flux is developed in the second loop. So you can see if you perform this in this integration, mu naught 4 pi, they all depends on the material type. And this dl1 and dl2, what is this dl1 and dl2? dl1 dl2 అంటే ఏంటంటే ఈ పాత్స్ మీద కట్ చేసిన స్మాల్ డిస్ప్లేస్మెంట్ వెక్టర్స్ రైట్ dl2 and dl1. So when you do the dot product, you're basically taking the dot product between the paths on this in this not in this I mean in this line on this line. At various points you have dl2 bar vector. On the same way on this line you have at various points you have dl1 bar vector. So when we perform this dot product, I can say this dot product basically depends upon the geometry. For example, if the loop was like this, first loop, and the second loop was like this, maybe you get a different answer. And if the loop, the first loop was like this and the second loop was like this, then maybe you get a different answer, right? So depending upon the shape of the loops, this integration is going to depend. Antegani does this integration does not depend on the current that is flowing. So I can say that this factor, proportionality factor, which is there, it depends only on the geometry of the two loops and the distance between the loops and all. So this factor is what we call as mutual inductance. So you can take any two loops and you can try to calculate the mutual inductance. For example, let me take a scenario here. Say there is first coil, which is a solenoid, and I know you know already through the solenoid the magnetic field is nothing but mu naught n into I. So here it is I1. Say around this solenoid, another coil is wounded, second coil, and the question is how much current flows through the second coil. Okay. So because we know that if the length of this coil is L1, okay, if the total length of this one is L1, so number of turn density, and say if there are N1 turns here, so N1 divided by L1 is the turn density, and because I1 current is going through it, so the field is uniform and the field is everywhere uniform. We can say it is mu naught N1 L by I1. So what is the flux? So what is the flux that is going through the second loop? Second loop lunch and the flux వెళ్తుంది అంటే b1 bar dot ds bar. Okay. So I can see that because if I assume the field is only inside and there is no field outside, so there is a uniform field cutting through the surface. So because in one single surface, if I take one single surface, the area of this surface is nothing but pi a square. Let us assume the second coil radius is a, and so the integration simply becomes area into the magnetic field b1. But because there are n loops, so second coil has n2 loops, so the total flux will be nothing but n2 times of area into the magnetic field strength. So if I substitute what is b1 here, so if b1 తీసుకొచ్చి ఇక్కడ substitute చేశాను అనుకోండి, then I can write it like this. So I can rearrange these terms. Okay, you can see whatever terms that are here. Okay, so these all terms depend upon the geometry. So number of loops you have in second one, number of loops you have in first one, and whatever area you have, this all depends upon I can say the geometry or how you build the second coil with respect to the first coil. So if this is the scenario, you can see this is a constant where we call it as mutual inductance between the second loop because of the first loop. So phi 2 is nothing but m2 times of I1. So you can see the mutual inductance here is completely dependent on the geometry of your material. Okay. So I can say this is your expression for mutual inductance. The same way, let us try to talk about self-inductance also. So let me take a loop and say there is already current I flowing through it. I say that just like for a for a loop for a secondary loop. So before ఇంతకుముందు చెప్తున్నప్పుడు రెండు లూప్స్ తీసుకున్నప్పుడు ఒక లూప్ అవుతూ ఒక లూప్ నుంచి కట్ అవుతున్న ఫ్లక్స్ విల్ బి ప్రపోర్షనల్ టు దెన్ అమౌంట్ ఆఫ్ కరెంట్ దట్ ఈస్ ఫ్లోయింగ్ త్రూ దిస్ అన్నట్టుగానే ఇన్ ద సేమ్ వే ది అమౌంట్ ఆఫ్ current for a given amount of current, how much amount of flux will be cutting through this loop anadi depends upon the inductance of your loop, right? So it depends on the shape. So this inductance depends on the shape of your loop, and the amount of flux that is cutting through that loop is basically proportional to the amount of current that is going through that loop at that instant, right? So varying current will produce a varying magnetic field, and that produces a varying magnetic flux which is opposed, right? So if you take a solenoid, say let us take a solenoid, kind of almost ideal solenoid where you can see the field is uniform everywhere inside, and outside the field is almost zero. So the current I of t is produces a time varying magnetic flux density within the solenoid. Together, because if I'm changing the current here, so that is going to create a magnetic field which is going to vary with time, and that magnetic flux change will induce an EMF, right, which induces a voltage across the solenoid. Okay, so let us see what happens is so for a continuous flow of charge, okay, so there should be a potential on the inductor. Okay, first of all, if you assume an ideal scenario, let us assume an ideal scenario that you have connected a battery and you have connected it to the battery. Okay, there is no resistance, so R is zero for this device. If that means what I have done, I have shorted the battery here because there is no resistance anywhere. Simply you have connected a wire, but you have curled the wire like this. So you have shorted the battery without any resistance. That means can there be any potential difference between these 2 points? అంటే ఇది షార్ట్ సర్క్యూట్ కదా సార్, ఈ రెండు పాయింట్స్ మధ్య పొటెన్షియల్ డిఫరెన్స్ ఏమి ఉండదా అంటే ఎస్ దేర్ ఎగ్జిస్ట్ పొటెన్షియల్ డిఫరెన్స్ అండ్ ఇట్ విల్ బి ఎగ్జాక్ట్లీ ఈక్వల్ టు ద పొటెన్షియల్ విచ్ యూ హ్యావ్ అప్లైడ్. వై ఇట్ ఈస్ సో, ఎందుకు అట్లాగా అంటే బికాజ్ ఇన్ ఆర్డర్ టు అపోజ్ ద వేరియింగ్ కరెంట్, ఓకే, the potential must be maintained. Okay, so what happens is uh, because the current cannot change instantaneously, it takes some time for a steady current to flow. And of course, if you don't disconnect the battery, it is going to drain out the battery because it has to continuously do a lot of work. Okay, and uh, so so here, usually from our Faraday's law, the loop integral about this path, which I choose of V bar dot dl bar is nothing but dou b by dou t of the flux, which is nothing but b of b bar dot ds bar. So you can see here that you can define the potential because your electric fields which are produced inside can be because of your battery, which are Coulombian kind of fields, and of course your battery is also applying some potential, we can say. And there is also an electromotive force, non-Coulombian force, which is trying to suppress the changing current. Okay, so those all things come under this integration. So with the minus sign, we can equate it to the potential V of t. So you can see that, for example, if I have a solenoid like this and the current is flowing in this direction, okay, so if the current is flowing like that, you can see that the magnetic field will be pointing in this direction. And because if the current is increasing, for an increasing current, you should need an opposing EMF. So what happens is, because you want to oppose it, so you need to oppose it in this direction. So you put your thumb in this direction, and you can see that your fingers will be curling like this, right? So that means if the current is trying to go like this, you are trying to oppose it by going in opposite direction. So దానివల్ల ఏమవుతుంది, సో there is an electrical non-Coulombian electrical force everywhere. So your Coulombian forces, which are nothing but because of your resistors and the surface charges, those Coulombian forces are trying to push the currents at every location in this way, ఈ డైరెక్షన్లో పుష్ చేయడానికి ట్రై చేస్తాయి. కానీ మీ నాన్ Coulombian forces, these EMFs which are generated, they're trying to push them in opposite direction. What happens is, because of this, there is some accumulation of charge, okay, and this accumulation of charge will come onto the surface and it slowly rearranges and it tries to compensate the field, the opposite field which is generated because of this EMF. and it tries to compensate it, and it tries to make the field uniform everywhere and pointing in the same direction. So in that way you can have a continuous flow of currents, but you can see that for that you have to fight with yourself, right? And then you have to maintain a constant current. So you can see that here I can say that dou b bar by dou t is nothing but, if there are n, for example, if there, instead of one loop, if there are n loops, then it becomes n times dou phi by dou t. I have just flux. So here, every time, instead of writing n times of phi at u, I'm going to use a Greek word sigma of t, which is nothing but flux linkage. We call it as. So I can say the amount of EMF that is generated is nothing but rate of change of the flux linkage, or usually we can write it as n times of dou phi by dou t. Okay, so what we can see here is, I can say that the amount of current that goes into the coil is proportional to the amount of flux linkage you have. Okay, so because as the number of loops are fixed, okay, and if you are increasing the current, that correspondingly increases the magnetic flux. So if the flux is increasing, the corresponding flux linkage also changes. So hence the proportionality factor. So the proportionality factor is what we call it as the inductance of L. So how much for a given change in current, how much change of this flux linkage is happening is given by the shape of your coil. Okay. So if you take the derivative on both sides, you can see that phi of t L is equal to dou I by dou t. So from here we get the expression, your famous expression for inductors, that is V of t is equal to L times of dou I by dou t. Okay. So you can see that what you have done is here. Okay. So inside your circuit, for example, if there is a circuit like this, okay, with a resistor and with a source, right? So let me take this as some some sigma, some epsilon, and this is L and this is R. Then I guess if you are asked to write the loop equation, it is nothing but minus sigma plus L into di by dt plus I into R is equal to 0 and Rajasthan. Okay. But actually, what you should write is, this is not the right way of writing it. What you have to write is minus sigma plus IR is equal to minus L times of di by dt. సరే ఏదన్నా ఒకటే కదా, ఇటుంటే అటుంటే ఏంటి అంటే, దిస్ వాట్ దిస్ ఇస్ సేయింగ్ ఇస్, because inside the loop there is a time varying magnetic flux. The two, if you go around the loop, okay, if you go around the loop, then the time varying magnetic flux will be exactly equal to minus L times of di by dt, which is the EMF that is generated. Okay, so you can see here that, so instead of creating this confusion and all, what we usually see in your textbooks is this VL component is already also brought inside your Kirchhoff laws, and it is made easy for you to evaluate. Okay. Anyways, uh, I guess this is the concept of inductance, how you get the formulas for inductance and all. You can always calculate the inductance for a solenoid, because for a solenoid you know the magnetic field, and phi is nothing but V times area of the loop. So you can see that the magnetic flux linkage is given by n times of phi. So once you know the magnetic flux linkage, you can actually relate it with the current, which gives you the inductance of your coil. So if you have a solenoid coil with n turns, I can say the ideal case formula is like this. So from this formula, if I see that if I increase the number of loops, my inductance will increase, or if I increase the area, then also my inductance will increase. And L, L another got important. Okay, it is not about the L, it is N per L. Okay, so if the turn density is increases, then also L increases. ఓకే, అంటే ఒకే సేమ్ లెంగ్త్లో ఇంకా ఎక్కువ టర్న్స్ని పెట్టాను అనుకోండి, అప్పుడు కూడా ఇండక్టెన్స్ని పెంచవచ్చు. సో దిస్ ఈజ్ అబౌట్ సెల్ఫ్ ఇండక్టెన్స్. Here is a video regarding the self inductance, where you can see that an inductor is connected across a resistor or some kind of device here, And you can see that because we know about the circuits, when you apply V omega t, and the current in the resistor will be same phase, but because if you but when you put an inductor, okay, the voltage and current will not oscillate at the same time instant. అంటే నువ్వు అప్లై చేయగానే ఇన్స్టంటేనియస్గా అదే డైరెక్షన్లో, అంటే అదే ఇన్స్టెంట్లో కరెంట్, అదే ఫేస్లో కరెంట్ కూడా స్టార్ట్ అవుతుంది. Okay, so your current starts with a phase difference which is given by omega L by R. Okay, I guess you can know it from your circuit theory. It is not a difficult one to do. Okay, so from here you can calculate what is your output voltage or output current, and you can see that there will be a phase difference of omega L by R. Okay, so you can see that because of this phase difference, the effects, the mechanical effects, are shown in this video. Okay, so let me play it.
The two. I can make you see in a quite dramatic way how strong self-inductances can fight their own current. And the way I'm going to do that is with a setup there, whereby I have a 12-volt car battery and I have two light bulbs. I have here an enormous self-inductance, L, 30 Henry. We will learn later in the course how you make such a high self-inductance. And then here is a light bulb. The light bulb has a resistance of 6 ohm. This self-inductance, there is nothing we can do about it, happens to have 4 ohm resistance. We don't have superconducting wires here. So it also has a resistance of 4 ohms. Forgive me for that, but there's nothing I can do about it. I have here another resistance of 4 ohms and a light bulb, which is the same one as that one, also 6 ohms. And then here is my car battery, plus a switch. And the car battery is 12 volts. And I'm going to throw the switch, turn it on. You will see that this light bulb comes on almost instantaneously. There is no self-inductance in this loop. Well, maybe a few microhenry or even less. But in this loop here, there is this huge self-inductance. And so the self-inductance says, take it easy to the current, take it easy, just wait, and you will very slowly see that light bulb come on. And we can calculate how long it takes. Because we have here 10 ohms, 6 ohms, and 4 ohms. So L divided by R is 30 divided by 10. So that is 3 seconds. So what that means is that even after 6 seconds, which is twice this time, even then, the current through this light bulb is only 86% of its maximum. But that means, since the light, of course, is proportional to I square R in the light bulb, that the light is only 75% of maximum. And even if you wait 9 seconds, then the light that comes out here is still only 90% of its maximum, whereas this one comes on immediately. The reason why we put the 4 ohm here, we want this part to be, from an ohmic resistance point of view, to be identical as this part. So that's why we artificially added here the 4 ohm, because the 4 ohm is always there in the self-inductance. There is nothing we can do about it. And so you're going to see a remarkable example. This is one light bulb. That is the one that is here. And this is the light bulb that is there. And the self-inductance is in this incredible monster here. I'll change the light setting a little bit so that we can see the light of the bulb. The bulbs are only 8-watt bulbs. They're not very, very strong, not very bright bulbs. But the effect will be very clear. So if you're ready for this, so this is the one that I think comes on immediately, and this is the one that takes its time. 3, 2, 1, 0. 1, 2, 3, 4, 5, 6. You see how slowly? It's still not very bright. Still getting brighter. It's still not as bright as this one. It's getting there. We can actually do some timing by counting. By the way, the values of the resistance that I gave you are when the light bulbs are hot. 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm still seeing it getting brighter. So what you're seeing here is a remarkable example that the self-inductance is fighting itself. That's why the name self-inductance is so nice.
Alright, so as you have seen the video, okay, so there is always some delay between the response because the current is being opposed. So, few interesting questions which I want to ask you is just like which we have discussed inside when we're dealing with capacitors. So, if you remember capacitors, while dealing with the capacitors, initially I have charged a capacitor, okay, and what I have done is I have removed, right, so I have charged the capacitor, and after that a charge was like this, so I used V1 and I said here it is Q1 and minus Q1, okay, and then I have disconnected the capacitors, and after that the potential, there is nowhere the current can go, but there is field inside between the capacitors, so the charge is block it there, and it is having some energy. And once we have increased the distance between the plates, now if the distance between the plates is increased, because v is equal to e into d in our scenario, because the distance was increased and the charges cannot change, okay, because the charges on the plates, okay, cannot change. So what happened is your in turn your potential has increased between the plates, so by increasing the distance, right? So and also coming to the capacitance, your capacitance where q is equal to c into v, I can say, because you can say your charge is not changing. So is your capacitance increasing? Into yes, it should, because your uh, v is increasing, your capacitance should increase, and because it will decrease because c is equal to epsilon naught a by d. So as d is increasing, you can see the resultant capacitance of this one, the capacitor has increased. So because it's a the distance between the plates is high now, the capacitance is a low capacitance. It has a capacity lesser capacity. So for the lesser capacity, in order to put that charge, your potential has to increase. Okay, so that is what we have seen there. So now in the same way, for example, if I take an inductor, okay, and I have connected it to a source, some battery source, okay. So an inductor will not be an open circuit. Okay, so if you leave an inductor like this, it behaves like a short circuit. Okay, that means after some time your battery will be gone. అంటే your బ్యాటరీలో ఉన్న మొత్తం చార్జెస్ అంతా మొత్తం డిశ్చార్జ్ చేసి పడేస్తుంది, మేబీ ఇట్ కెన్ బ్లో అప్ ఆల్సో. సో అందుకని ఏంటంటే సే ఫర్ ఎగ్జాంపుల్ we have connected the uh, inductor for some time, okay. Say you have connected your battery like this and there is a switch like this, say for t is equal to some 5 seconds or so you have connected, and after that you have removed it, okay. Now what, when you have removed the supply, okay, now you have an inductor like this now. So if I now ask you the question that, if I now with an inductor like this, if I now increase the number of loops, so అదే వైర్ని ఇంకొన్ని లూప్స్ ఎక్స్ట్రా చేసి ఇట్లా పెట్టాను అనుకోండి. So now if I increase the loops, the question is, will the inductance increase or not? Yeah, definitely if the wire has more loops, the inductance will increase. So if the inductance is increasing, because phi is equal to L into D, right? Because flux, the amount of flux that is going is nothing but L into I. Okay. And moreover, we say that inside the inductor, B is nothing but is equal to mu naught n divided by I. So the turn density has increased or what? Because in the same length now you are putting more loops, so definitely this has increased. So will the magnetic field increase or not? And correspondingly, నేనేమంటా అంటే will the flux is increasing, ఓకే, బికాజ్ ఇక్కడ ఇండక్టెన్స్ పెరిగింది, ఓకే, ఫ్లక్స్ కూడా పెరిగింది, అంటే కరెంట్ మారలేదా? సో డస్ ద కరెంట్ డజంట్ చేంజ్. First of all, is there any energy stored inside the inductor or not? Okay, is energy stored inside the inductor or not? ఇంతకుముందు ఏంటంటే మీరు డిస్కనెక్ట్ చేసినప్పుడు there is electrical energy stored here. But if you disconnect a inductor, will there be any electrical energy stored or not electrical energy? Particularly, will there be any magnetic fields or magnetic energy that is stored inside? అంటే ఏం ఉండదు. Means it will discharge in, అంటే ఏం జరుగుతుందంటే బికాస్ కెపాసిటర్కి ఇండక్టర్కి అదే డిఫరెన్స్ నాన్న. సో వెన్ యూ కనెక్ట్, వెన్ యూఆర్ ఛార్జింగ్ ఎట్ అంటే వెన్ యూఆర్ సెండింగ్ కరెంట్, సో ద ఫ్లక్స్ ఇస్ డెవలపింగ్ హియర్. సో స్లోగా ఏంటి అంటే ఇందులో ఫీల్డ్ డెవలప్ అవుతుంది. సో ఆ డెవలప్ అవుతున్న ఫీల్డ్ని అపోజ్ చేస్తుంది. ఆ అపోజిషన్నే సెల్ఫ్ ఇండక్టెన్స్ అంట. సో వన్స్ యూ సడన్లీ బ్రేక్ ద స్విచ్, నువ్వు స్విచ్ని కానీ బ్రేక్ చేసావు అనుకో, సో నువ్వు బ్రేక్ చేయగానే ఇన్స్టంటేనియస్గా కరెంట్ని జీరో చేసేస్తున్నావు సర్క్యూట్లో. అలా చేయనివ్వదు, అలా ఒప్పుకోదు సర్క్యూట్. యువర్ ఇండక్టర్ డస్ నాట్ లైక్ ఫర్ ద కరెంట్ టు గో సడన్లీ జీరో, బికాస్ ఇఫ్ ద కరెంట్ గోస్ టు జీరో, వెంటనే మ్యాగ్నెటిక్ ఫీల్డ్ షుడ్ గో టు జీరో. దట్ మీన్స్ దెర్ ఇస్ ఇన్ఫినైట్ చేంజ్ ఆఫ్ ఫ్లక్స్. సో దట్ షుడ్ నాట్ హ్యాపెన్. సో అందుకని ఏం చేస్తుందంటే వెన్ యూ సడన్లీ బ్రేక్ ఎ స్విచ్, ఓకే, ఇండక్టర్ రియలైజెస్ దట్ యూ హ్యావ్ నువ్వు కనెక్షన్ పీకేసావు అని దానికి వెంటనే అర్థమవుతుంది. సో అది వెంటనే అపోజ్ చేస్తుంది. అపోజ్ చేయడం అంటే ఇప్పుడు దాకా కరెంట్ ఇలా ఫ్లో అవుతుంది, ఆల్ ఆఫ్ ఎ సడన్ ఎప్పుడైతే నువ్వు స్విచ్ బ్రేక్ చేసావో వెంటనే ఆపోజిట్ డైరెక్షన్లో కరెంట్ని తోటి స్టార్ట్ చేస్తుంది. సో ఆ కరెంట్ తోసినప్పుడు, ఫర్ ఎగ్జాంపుల్, ఇఫ్ ఇట్ సీస్ అన్ ఓపెన్ సర్క్యూట్, వాట్ హ్యాపెన్స్ ఈస్ బిట్వీన్ దీస్ టూ టెర్మినల్స్, ఓకే, a huge potential will develop, a huge EMF will develop. We call it as back EMF. అంటే ఏంటంటే నువ్వు సడన్గా స్విచ్, సే ఫర్ ఎగ్జాంపుల్ ఈ స్విచ్ ఓపెన్ చేయడానికి, టు ఓపెన్ స్విచ్ you take very small amount of time, అంటే within 1 nanosecond or maybe within 1 millisecond you have opened the switch. సో అలా ఓపెన్ చేయగానే, బికాస్ దెర్ ఇస్ అ సడన్ డిక్రీజ్ ఆఫ్ కరెంట్, your inductor doesn't want the current to decrease, so the current has to decrease now. So for a decreasing current, in order to support it, it starts to pump current. అంతే కదా, ఇప్పుడు ఇండక్టరే కరెంట్ పంప్ చేయడం స్టార్ట్ చేస్తుంది. ఇంతకుముందు బ్యాటరీ పంప్ చేసేది కరెంటు, ఇప్పుడు ఇండక్టరే పంప్ చేస్తుంది. ఇండక్టర్ దగ్గర కరెంట్ ఎలా వచ్చింది? ఇండక్టర్కి కరెంట్ చేసే టాలెంట్ కూడా ఉందా, కరెంట్ని పంపించే టాలెంట్ కూడా ఉందా అంటే, యా, ద వేరింగ్, అది కరెంట్ ఎందుకు ప్రొడ్యూస్ చేయగలిగింది అంటే, ఇప్పుడు ఇండక్టర్ ఈజ్ యాక్టింగ్ లైక్ బ్యాటరీ, ఇట్ ఈస్ పంపింగ్ అవుట్ కరెంట్. ఎందుకు పంప్ చేస్తుంది అంటే, బికాస్ కరెంట్ తగ్గిపోతుందని తెలిసి సర్క్యూట్లో ఆ లూప్లో ఏదో విధంగా మ్యాగ్నెటిక్ ఫ్లక్స్ని తగ్గనివ్వకుండా చేయడం కోసం ఆపోజిట్ డైరెక్షన్లో an EMF is induced, and that EMF is actually making the current to run in opposite direction. So once this happens, if it is an open circuit, huge potential will be developed between these two terminals, and that can create a spark. ఎప్పుడైతే ఆ స్పార్క్ క్రియేట్ అయిందో దానివల్ల ఏమవుతుందంటే, ఆ స్పార్క్ వల్ల ఆ పాత్ నుంచి మొత్తం కరెంట్ అంతా డిశ్చార్జ్ అయిపోయి, స్లోలీ వాట్ హ్యాపెన్స్ ఈస్ యువర్ ఫీల్డ్ ఇన్ సైడ్ విల్ డిక్రీజ్. ఓకే, ఎందుకంటే ఆ కరెంట్ అపోజ్ చేయడం ట్రై చేస్తూ ఉంటుంది, కానీ ద కరెంట్ హ్యాస్ టు గో టు జీరో బికాస్ ఇట్స్ అన్ ఓపెన్ సర్క్యూట్. సో స్లోలీ అండ్ స్లోలీ ఇట్ లూజెస్ ఇట్స్ ఎనర్జీ ఇన్ ద మ్యాగ్నెటిక్ ఫీల్డ్ బికాస్ ఆఫ్ ది స్పార్క్ అండ్ ఆల్. ఆర్ ఇఫ్ ఎట్ ఆల్ యూ కనెక్ట్ ఎ రెసిస్టర్, సో ఎప్పుడైతే మీరు స్విచ్ ఓపెన్ చేశారో అక్కడ ఫర్ ఎగ్జాంపుల్ ఏదైనా రెసిస్టర్ పెట్టారనుకోండి, ఇట్ డిసిపేట్స్ త్రూ ద రెసిస్టర్. ఆర్ ఫర్ ఎగ్జాంపుల్ ఇఫ్ దెర్ ఈస్ నో రెసిస్టర్ ఆల్సో, usually we say that there are some parasitic capacitance, capacitive effects between the terminals. Okay, we say there is some parasitic capacitance. So maybe the magnetic energy converts into the electrical energy and it goes into the capacitive effects, parasitic effects, అంటే ఇక్కడ చార్జెస్ డెవలప్ అయిపోతాయి బాగా. Or it can oscillate between the fields, అంటే ఎనర్జీ ఏంటంటే it can bounce off between the parasitic capacitance and the inductance you have, and some oscillations can happen. But what happens is that after some time, because of some amount of resistance, it slowly starts to lose the energy in the magnetic fields. So so this kind of distinction you need to understand between the capacitor and inductor, that uh, that capacitor can store energy even if you connect it, disconnect the supply, right? But inductor, it will not. Okay, it loses the energy in somehow. So what is the energy that is present in the magnetic fields? And as I was previously saying, when we are seeing the scenario, say if there is a current carrying wire like this, and there is a magnetic field which is coming out of the, which is going into the board, and you can see in this region there is a magnetic field. So from the equation, force is nothing but this dl bar cross I bar cross B bar, right? So R we have written as I into dl bar cross. So if you know the current direction, the force is nothing but the cross product between the current and the magnetic field which is going to the board. So from with your right hand, if you do I cross B, I in this can be you can see your thumb will be pointing in upward direction. So what happens is there is a force on this loop which is pulling it upward direction. Okay. So because the wire is also moving in this upward direction, so the resultantly there is some work done. Okay, so if you ask me what is the work done here, so the work done is nothing but force into the amount of distance it has traveled. So for example, if I say this is as y-axis, so if the distance traveled is dy, so you can see this is the amount of work that is done. Okay, so can magnetic field do work? And we talked about it, right? We will not do any work on the this charges, but you see that the magnetic field will be uh, responsible for work. Okay, and who is doing the work? And particularly ఈ వైర్ అనేది పైకి వెళ్తున్నప్పుడు ఎవరు వర్క్ చేస్తున్నారంటే దిస్ వర్క్ is actually done by the current source. So why current source is doing the work? ఈ వైర్ కాదా వర్క్ చేస్తుంది అంటే నో, ద వైర్ ఇస్ నాట్ డూయింగ్, ద మ్యాగ్నెటిక్ ఫీల్డ్ ఇస్ నాట్ డూయింగ్ ఎనీ వర్క్ హియర్. Okay, the field is responsible. We saw that because of the Hall effect, an alternative induced electric field will be there on the positive core, and that actually basically pulls it up. So in order to maintain that potential and everywhere, so you need to, for having a continuous current flow, your current source has to put up that work. Okay, and in fact if you see this work done also, you can see I can rearrange the equations here. So b into I and a into dy and a into a into dy is nothing but a is this area and dy is the extra distance you have traveled. So a into dy is nothing but the amount of extra area you have covered when you move up. Okay, so this extra area into the magnetic field is nothing but the extra flux you see. So I can say the amount of energy you get is nothing but, or ఇక్కడ who is doing the work. So ఇక్కడ వర్క్ చేసినప్పుడు some energy is lost. Okay, so how much energy is lost I can also say is nothing but the current times of the rate of change of the flux. I mean how much amount of flux changes have, not rate, I mean how much amount of flux change has happened. So if I see at these scenarios, okay, so in order to అంటే ఒక సర్క్యూట్లో కరెంట్ బిల్డ్ చేయాలి అంటే స్లోలీ యు ఆర్ బిల్డింగ్ మ్యాగ్నెటిక్ ఫీల్డ్ ఇన్ ద సర్క్యూట్. సో ఇన్ ఆర్డర్ టు బిల్డ్ ఎ మ్యాగ్నెటిక్ ఫీల్డ్ యూ హ్యావ్ టు డూ వర్క్. ఎందుకంటే ప్రతిసారి నువ్వు స్లోగా కొంచెం ఫ్లక్స్ ఇంక్రీజ్ చేసే కొద్దీ ప్రతిసారి ఇఫ్ యూ వాంట్ ఇంక్రీజ్ ద వర్క్ ఫ్రమ్ వన్ పాయింట్ అనదర్ పాయింట్, someone has to do work on the system. In the system someone has to perform work. So, or else say for example, if your magnetic field is decreasing also, magnetic field తగ్గుతున్నా కూడా, then also someone has to do the work because a decreasing magnetic field will be opposed. అది అపోజ్ చేస్తూ ఉంటుంది కాబట్టి దానికి ఎగ్నెస్ట్గా ఎవరో ఒకరు వర్క్ చేస్తూ ఉంటారు. అలాగే ఒక మ్యాగ్నెటిక్ ఫీల్డ్ని తయారు చేయాలన్నా కూడా ద నేచర్ ట్రైస్ టు అపోజ్ ఇట్. సో సమ్మన్ హ్యాస్ టు డూ వర్క్ ఇన్ ఆర్డర్ టు క్రియేట్ సచ్ కైండ్ ఆఫ్ మ్యాగ్నెటిక్ ఫీల్డ్స్. సో వెనెవర్ యూ డూ వర్క్, మీరు వర్క్ చేసి మ్యాగ్నెటిక్ ఫీల్డ్స్ క్రియేట్ చేసినప్పుడు దట్ ఎనర్జీ ఇస్ నథింగ్ బట్ స్టోర్డ్ ఇన్ సైడ్ ద ఎనర్జీ ఆఫ్ ద మ్యాగ్నెటిక్ ఫీల్డ్స్. మ్యాగ్నెటిక్ ఫీల్డ్ ఎనర్జీ కింద స్టోర్ అవుతుంది. So once you are trying to decrease the magnetic fields, so the magnetic fields gives you out the energy. Okay, అంటే మీరు మ్యాగ్నెటిక్ ఫీల్డ్ తగ్గించడానికి ట్రై చేస్తున్నప్పుడు మ్యాగ్నెటిక్ ఫీల్డ్స్ వాటి దగ్గర ఉన్న ఎనర్జీ తీసుకుని ఈ ఫీల్డ్ తగ్గిపోకుండా అపోజ్ చేయడానికి ట్రై చేస్తాయి. ఓకే, సో so in that scenario your magnetic field loses energy. So once your magnetic field is gone, then there is no longer energy inside the space regarding the magnetic fields, right? So, so any work done is usually depends upon the amount of flux change you are trying to plan. So for a given current, how much flux you want to change decides how much work you are doing to do. Okay. So if phi 1 and phi 2 are the initial and final fluxes of the current loop, if there are n loops like that, then the total flux, the total work done is nothing but the amount of flux change you are planning or flux linkage you are planning. So usually the amount of flux change is that gives you the small increment in the work you are doing. Okay. So for example, let me take a scenario for an inductor. Okay, for an inductor, we said the amount of flux is proportional to the amount of current that is passing through that coil, which is given by L times of where L is a number which depends upon the geometry of the material. So if you are trying to change the flux, so అంటే కరెంట్ పెంచడం ట్రై చేశారు అనుకోండి ఫ్లక్స్ పెరుగుతుంటుంది. So for a change in how much change in flux will happen? Okay, so from here you can see that uh, the amount of work you have to do to increase current in an inductor అంటే ఏదైనా ఒక లూప్లో కరెంట్ పెంచాలి అంటే to change the current, how much work you have to do అంటే the work I have to do is nothing but I times of the flux I have to change. So if I change, take the derivative of d phi, because inductor is not going to change, so it simply becomes L times of di. So it is nothing but L times of IDI. So this is only a small incremental work if you want to increase a current by small value di. But say you want to increase the current from 0 to I, okay, you have to do a total work of, you do an integration from 0 to I, you get an answer of half Li square. So you can see this half Li square formula basically comes from the fact that whenever you want to increase the flux or you want to change the flux in any loop or any circuit, you basically have to do work, and that work is stored as an energy inside your magnetic field. So what is the energy inside a magnetic field means you can actually use this expression that the rate of the amount of work you do is nothing but the current times of change of flux. You can use this expression, and because flux is nothing but you can express flux as integral a bar dot dl bar, and from those equations you can derive this equation that if you have some kind of current density inside a volume j bar, okay, j bar and a current density ఉందనుకోండి, in order to create this current density, ఇలాంటి కరెంట్ డెన్సిటీ ఒకటి తయారు చేయాలంటే కూడా నువ్వు చాలా వర్క్ చేయాలి. అంటే if you want to put some current in a wire, you have to do some work, because without doing any work the current will not flow easily. Okay, అంటే if you are trying to put some current density in some region, you have to do some work, and how much work you will be doing, whatever work, just like electrostatics లో చెప్తున్నప్పుడు, if you want to assemble charges in a volume, ఏదైనా వాల్యూమ్లో కొన్ని చార్జెస్ని ప్లేస్ చేయాలనుకోండి, some charge, if you want to create some charge density, you have to do some work. How much work you have to do అంటే అక్కడ కూడా ఎట్లానే వచ్చింది, హాఫ్ టైమ్స్ ఆఫ్ వాల్యూమ్ ఇంటిగ్రేషన్ ఆఫ్ రో టైమ్స్ ఆఫ్ పొటెన్షియల్ ఇంటూ dV. సో దిస్ ఇంటిగ్రేషన్ వాస్ డన్ ఓన్లీ ఆన్ ద రీజన్ వేర్ యూ హ్యావ్, అంటే నీ సోర్స్ ఎక్కడుందో ఆ రీజన్ మీద చేసిన వాల్యూమ్ ఇంటిగ్రేషన్. అట్లానే ఫర్ ఎగ్జాంపుల్ యూ ఆర్ ట్రైంగ్ టు డెవలప్ సమ్ కైండ్స్ ఆఫ్ కరెంట్స్ ఇన్సైడ్ ఇన్ ద స్పేస్, ఎక్కడో కరెంట్ డెన్సిటీస్ని తయారు చేయాలనుకుంటున్నారు అనుకోండి. In order to create those current densities, you have to do this much amount of work, where your volume integration is the volume integration on the source. But just like in electrostatics, you can convert this integration by a mathematical technique by parts, and you can write this integration over all space. Here also you can write the integration over all space, and you can say that what is the work you have done, or what is the energy that is present in the fields, means whatever work you have done to create this kind of current densities, it basically goes into your system, right? The energy goes into your system, and your system contains this magnetic fields. So the amount of energy that is present inside the magnetic field is nothing but half times of overall all space v bar dot h bar. Just like your electrical energy is half times of volume integration of all space e bar dot d bar, okay, dv, right? So this is how you can treat the magnetic energies.